I'm Peter.
I'm Mason.
I'm Khoi.
And this is our AP Physics 1 Lorfing Fluids.
I'm going to show you guys how buoyancy force works. And the buoyancy force equation is density times volume times gravity. Let me show you guys a real life example.
Hey, it's Peter here, and before we move on, I just want to quickly explain Archimedes' principle a little bit more. Now, the equation states that P, the density of the fluid, V, the volume of the displaced fluid, and G, the acceleration due to gravity, are all directly correlated. This means that an object of greater volume will displace a larger volume of fluid, and thus have a larger buoyancy force acted upon it when compared to an object of smaller volume when placed in the fluid of the same density. Now, this example provided will explain that concept.
Both objects are made out of clay. Both weigh 50 grams, but only one of these two is actually going to float. And you probably guess which one's going to float or sink. Let's start with the clay ball. Let's place it in this overflow tank, this displacement tank. And not surprisingly, it sank like a rock. And a bunch of water is coming out on this end. How much water comes out? Well, if we wait long enough for all the water to drip out that would drip out, it would come out to about 30 milliliters on our graduated beaker. That is equal to the volume of this clay ball, that is how much space it takes up. But what we're really interested in today is not something sinking, but more about why is something floating. So let me fish this ball out of the water. And this time, let's float the clay boat. Now to do this precisely, we have to pour this water back in, so we're back at 0. Because really, you can look at this like a digital, or not digital scale, but a water scale. I need some helping hands to help place this boat. I've got little hands here. Let's carefully lay this on top of the water. And look at this. It's floating, and it's pushing out a volume of water. Now this time, the amount of water that comes out on this side is not going to be 30 milliliters. It should be 50 milliliters at least, if Archimedes was correct.
Now that that's out of the way, back to the video.
Let me show you guys a real life example. Right now, in the system of me, the weight, and the earth, there's only two forces. The force that apply to the weight and the gravity. Right now, as you can see, I'm like struggling to lift this weight because of how strong the gravitational force is. Now let me show you guys buoyancy force in the water. Let me show you guys buoyancy force in water. On land, there are only two forces that I was lifting with the weight. There's gravitational force and applied force that I was lifting up. Hard and water, there's three forces. There's the gravity force, the buoyancy force is the upwards, and the applied force I'm lifting up. On land, it is harder to lift the weight up because of the gravitational force. However, in water, this buoyancy force is helping me lift the weight up. Now let me show you guys a demonstration. As you can see, it was so light to lift that weight because of the buoyancy force lifting upwards with the applied force lifting upwards me. So the buoyancy force and the upward force applied was greater than gravitational force.
Hello, my name is Mason. Today, I'm explaining to you the continuity equation. The continuity equation states that area 1v1 is equal to A2v2. Okay, so what that means basically is that...
Okay, it's Peter again. Now, let me professionally take you through the continuity equation. Now, the equation states that A1, the initial area multiplied by V1, the initial velocity or speed of the fluid, is equal to A2, the final area multiplied by V2, the final velocity or speed of the fluid. This means that when a fluid is traveling through a pipe, the product of the area and the velocity will remain constant. If the area of the pipe was to shrink as shown in the image, then the velocity would increase, representing an indirect relationship between the two variables. Now let's look at an example which proves this relationship. We got a ruler, a container for the water to spill in, and then two stacks, and two water bottles. One water bottle is going to have a small hole on the bottom. We're going to fill it up with water, and then water's going to spout. Another hole is going to have a big hole in the bottom, and water's going to spout. Okay? Now I filled it right up at this line, and we're going to release and see how far it goes. Oh! Okay, so I filled it with the same amount of water, and now we release. God. Okay, after reviewing the footage for both one, the small hole went a total of 9.5 inches, while the larger hole traveled around 7 inches. Now, the equation for velocity is distance over time. Now, because time is irrelevant, because we're looking at the same time for both trials, that means we only look at distance. And because there was a larger distance for the smaller hole, that means the smaller hole had a larger velocity when compared to the larger hole, which had less of a velocity, which proves the equation a1v1 is equal to a2v2. And back to the video.
See, from here, I'm about to demonstrate it, but this has a large area, right? So when I dump it out like this, the water flows out like that, correct? That was very slow. That's because there's a larger area, meaning that there would be a slower velocity. Now when I shoot it, as you can see, it takes from this little white clear tube right there. It takes the water from there, and it streamlines it into this small little nozzle, right? So what that means is that small area will increase the velocity of this water gun. So rather from going from this large area, it goes into this small area. This is the continuity equation of fluids in Physics 1. Thank you.
Hello there. Let's talk about gauge pressure. Gauge pressure is the pressure that you feel when you're under the water. The equation for gauge pressure is density times gravity times the change in y, or depth. As I go further down this pool, I'll feel an increase in gauge pressure as more water is above my head. When I come back up, my ears pop as the pressure is relieved. When I was down there, it was a lot of pressure, so my ears were being condensed and they hurt. But as I come back up, all that pressure is gone. So that's gauge pressure.
Hello everybody, I'm going to explain how density works. Density is how much mass is packed in a given volume, such as this object. As you guys all know, if the object has a lower density than the water, it will float. But if the object has higher density than the water, or the same density as the water, it will sink. Let me show you guys a demonstration. I'm going to drop these two water balls. One water ball has small density, while this water ball has full density of the entire bottle. Now I'm going to drop it. Are you guys ready? 3, 2, 1. As you can see here, the water bottle with less density is floating because it has less density than the water. But if you look down here, it sinks, bro. It sinks because it has the same density as the water, or greater density than the water. That is density.
Name: Mason Quacken. Principal: Bernoulli's.
You already know who it is. Bernoulli's equation states that P1, or the initial pressure, plus 1/2 PV squared, the initial fluid equivalent of kinetic energy, plus PGH, or the initial fluid equivalent of potential energy, is equal to the constant, or in other words, the same variables in their final state. In simple terms, Bernoulli's principle states that fast-moving air or liquids exert less pressure than slow-moving air or liquids. Now, let's take a look at this example.
Air is flowing here, and right here, where there's very little room, the air will have very high speed, way higher than it has where it has lots of room. And so, at the highest speed, you get the lowest pressure. And so the ping pong ball is sucked in while you're blowing it. And to give you the conclusive proof of that, I will do it this way. I will put the ping pong ball like so. And I'm going to blow like this. And if I blow hard enough, ping pong ball will stay in there. Because I generate a lower pressure right here where the passage is the smallest. But I have to blow quite hard. See that? Isn't that amazing?
Okay, now back to the video.
Bernoulli's principle states that higher velocity fluids create low pressure areas. What low pressure areas will do is attract high pressure. And what you're about to see is a flat. Let me demonstrate. What you saw there was Bernoulli's principle in action. Let me demonstrate to you what a low velocity fluid would do. Saw that? No flat. Therefore, Bernoulli's principle is true.